stoichiometry. So, like I said, that's probably spelled wrong. What is stoichiometry? It's calculations of reactants and products based on a balanced chemical reaction. So the reason we even learned about balancing by adding coefficients, making sure the atom count was the same on both sides, was that we could use that balanced chemical reaction to do calculations with. So we learned how to do calculations at the beginning of this chapter, going between grams, moles, and particles. So we're going to be taking that and applying it to a balanced chemical equation. Now, when we're looking at a balanced chemical equation, the coefficients, those numbers that we change to make the atom count the same, these numbers represent the number of moles. What that means is for this equation that I have up here, there is 1 mole of C3H8 reacting with 5 moles of oxygen. And what that's producing is 3 moles of carbon dioxide and 4 moles of water. Do you remember what type of reaction this is?
This is a
Combustion reaction, yes. So we have a hydrocarbon reacting with oxygen, which is the fuel, making carbon dioxide and water. So what types of questions could you be asked based off of this balanced equation? One of them, we're going to start with 1-step ones, and then we'll work our way up to the harder ones. So the first type of question you might see is, how many moles of C3H8 will react with 3 moles of O2? So they're asking you to look at the coefficients to figure this out. We just said that if you had 1 mole of C3H8, that would react with 5 moles of oxygen. Okay, but they're not asking for 5, they're asking what if you only had 3. So to figure this out, you're going to use a mole ratio. What mole ratio? Well, you're looking at the coefficients, because the coefficients represent the number of moles, and you're looking at the 2 they're asking about. What I mean by that, you're looking at C3H8 and you're looking at O2. So you're going to use the mole ratio just like a conversion factor. Looking at the number or the coefficient in front of C3H8 is a 1. So that means 1 mole of C3H8 is going to react or equal to, and now I look at oxygen because that's what we're comparing it to. And there's a 5 in front of it for the coefficient, and since the coefficients represent the number of moles, that is 5 moles of O2. So I write a mole ratio just like I would write a conversion factor using those coefficients to represent the number of moles. So this is going to be the conversion factor that I'm going to use to solve this problem. When I get started, when I do my railroad tracks, remember we always start with the piece of information given in the question. And the only number they gave in the question was this 3 moles of O2. So if I write my railroad tracks, I'm going to start with 3 moles of O2. The question is asking me to solve for moles of C3H8. So this conversion factor will get me there. Do I want the 5 moles on the top or on the bottom? Bottom. It's the same theory that we did before. You're trying to cancel out what you don't want and keep what you do. So we're going to put the 5 moles of O2 on the bottom so that moles of O2 are opposite sides of this horizontal line, canceling out. And that's going to put the other part of the conversion factor, the 1 mole, C3H8 on the top. Remember, these vertical lines are just multiplication, and then you're going to divide by whatever on the bottom. So 3 times 1, and divided by 5. And since they only had 1 sig fig in the question, we would have just 1 in our answer. I get 0.6. I get something different. And that is moles of C3H8. So, If you had 3 moles of O2, you would need 0.6 moles of C3H8 to react with that. Okay, we're going to use this same balance equation, but I'm going to ask a different question on it. Question do I have next? So let's try a little harder. This time we're going to start with moles, so we'll have 2.91 moles of O2. We're going to go to grams. We produce how many grams of, let's do water. So remember, the coefficients are representing the number of moles. And what this 5 in front of the O2 is saying is there are 5 moles of O2. But the question is asking, okay, what if you didn't have 5 moles? What if you had 2.91? Then how much water would you produce? So to figure this out, we need to come up with some conversion factors. And the 2 coefficients that we're going to focus on are the coefficient in front of O2 and the coefficient in front of H2O. So we're comparing these 2 this time. So in order to go from moles of O2 to water, we need to look at the coefficients in front of it. So that coefficient of 5 in front of oxygen is saying 5 moles of oxygen. So if I had 5 moles of oxygen, it would produce 3 moles of CO2 and 4 moles of H2O. I'm only comparing it to the water in this case, so I'm going to set it equal to water, and more specifically, 4 moles of water, because that 4 in front of the H2O represents the number of moles. So this conversion factor is going to get me from moles of O2 to moles of water. Okay, it's the same step that we did in the last problem. But notice, we can't just stop there because it's not asking for moles of water, it's asking for grams. So we have another step here. Okay? So the next step is going to be to get to grams of water. For this first step, going from moles of oxygen to moles of water, we're using the mole ratio that we have written right here. Right? This will get us from moles of O2 to moles of water. Now this next step, going from moles of water to grams of water, this is kind of a review from the beginning of the chapter. We went from moles of water to grams of water before. Do you remember what we needed to use to get there? So we have Avogadro's number that gets us from moles to particles, or atoms, or molecules. But to get from moles to grams, we have molar mass. So molar mass, we can calculate the molar mass if we know the chemical formula. When we calculate molar mass, the units are grams per mole. So that is used as a conversion factor to get us between grams and moles. So if I need the molar mass of water, I'm going to calculate that off to the side, because that's going to be my conversion factor that's going to get me from my moles to my grams. So a little bit of a refresher. To calculate molar mass, you use the chemical formula, you make a list of each atom present, and then you take the number of each atom or element and multiply it by the molar mass from your periodic table. Does anyone need a periodic table? Have extras. I know there's one up here on the board, but this is the one that we'll be using. Anyone want an extra one? You want one?
Take one for now.
Never have too many. All right. So for water, we have hydrogen and we have oxygen. So to figure out the number of atoms, you're looking at the subscripts. So how many hydrogens do we have?
2,
2. How many oxygens?
1,
Just 1. Okay. Now, for the second part, the molar mass, you look up hydrogen on the periodic table and find what its average atomic mass is. 008, and then oxygen,
16.
multiply across, and then add it all together.
8.016. Oh, sorry.
18, right?
Yeah, I forgot the one.
So the molar mass of water is 18.016 grams per mole are the units. Now, just like when we did the dosage lab, whenever you see a slash, you can write this differently as a conversion factor. So that's what I'm going to do. I'm going to write it up here. I have 18.016 grams, and then per 1 mole. So I'm going to set that equal to 1 mole. So that means if I had 1 mole of water, and I weighed it out on the scale, it would weigh 18.016 grams. So these are our 2 conversion factors that are going to get us from moles of oxygen all the way to grams of water. So once you have your conversion factors, you can start your railroad tracks. What do I want to start my railroad tracks with, though? What piece of information? 2.91. You start with the number given in the question itself. So we're going to start 2.91 moles of O2. And the reason I'm writing moles of O2 is because since we're going between 2 different molecules, I want to keep track of which one I'm at. Okay? So we have moles of O2. We're going to have to use the mole ratio first to get from moles of O2 to moles of water. What do I want on top? Moles of water. So I'm going to put my 4 moles of H2O on top, and then I'll put the 5 of O2 on the bottom. That way, moles of O2, opposite sides of the horizontal line, cancel. So if I stop now, I would be in moles of water. But I want to keep going and get to grams, and I'm going to do that by using my molar mass. So for this one, I want grams on top. So that's what I'm trying to keep. So I'm going to put my 18.016 grams of water on the top, and my 1 mole water on the bottom. So the moles of water cancel. So now, 2.91 times 4 times 18.016, all of that divided by 5.
1.9412.
How many sig figs did we want?
3.
3. Look at the original number. Okay, we're not using the conversion factor numbers. So 3, so what would the answer be to 3 sig figs then?
42.0.
2.0. So what this says is, if I had 2.91 moles of oxygen, that's how much I used, that's how much I put into the flask to get the reaction, I would produce, or I would make 42 grams of water. So scientists do calculations like this on a daily basis because when they're trying to make a certain amount of something. This tells them how much of the reactants to put in a flask to get a certain amount of product out. Okay, now we went from moles to grams. Now, when chemists go and do a reaction, they can't mass out moles. They mass out grams. So we're going to do another problem, taking it a step further. We're going to start with grams of a reactant and go to grams of a product. So this is the longest type that you'll see. So I'm going to use the same reaction. We'll do another one. I'll change the balanced chemical reaction in a minute. I just want to do one more with using this one. And we're going to say, let's say we had 1.15 grams of C3H8. So that's one of the reactants. So that's how much I massed out on the scale. And I want to know how many grams of CO2 would be produced. So that's how much reactant I started with. How much CO2 would be produced. It's one of the products. So I'm going to start by writing my plan, and then I'll figure out all of the conversion factors that I need to solve. So what are we starting with? Grams of C3H8. So that's going to start my plan. Now, I want to get to grams of CO2, but I can't go from grams of C3H8 directly to grams of CO2. That doesn't work. The only way I can get to CO2 is I need to get into moles first, because the coefficients in front of each of these elements or compounds represents the number of moles. So if I'm trying to go between two different compounds, I need it in moles in order to do that. So my first step, if I'm in grams, is to get into moles. Then I can use a mole ratio to compare. So the first step is going to be to go to moles of C3H8. Because I have to have it in moles in order to compare. Because that's what those coefficients mean. They are the number of moles. So if I can get into moles of C3H8, now I can compare two different elements or compounds to each other using the balanced chemical equation. So once I have moles of C3H8, remember I'm trying to get all the way to grams of CO2, so my next step will be to get to moles of CO2 using the mole ratio. But I need to keep going. I don't want to stop at moles, I want to get into grams, so I have one more step to get into grams. So, lots of steps. Let's figure out what pieces of information we need for each step, so we can make a list of all of our conversion factors before we start trying to solve. So here, first step, I'm going from grams to moles. What do I need to get between grams and moles? MM, molar mass. Yep, so this is going to be molar mass. So that means I have to calculate the molar mass of this compound, C3H8. I'll do that in a minute. I want to go through and see everything I need first. So molar mass, since it's measured in grams per mole, will get us between the grams and the moles. Now this step, now we're going between moles and moles. But it's moles of one compound and moles of a different compound. So for this, you're using the balanced chemical equation. And we're going to use a mole ratio. Since these coefficients represent the number of moles, we'll be comparing the coefficient in front of C3H8 to the coefficient in front of CO2. Last step, going between moles and grams. So what do we need to go between moles and grams? MM, molar mass again. Okay, but it's molar mass of a different compound. Now we're talking about CO2. So let's calculate that first step. We said we needed molar mass, more specifically molar mass of C3H8. So I'm going to calculate that by making my list. Oops, that's a 3. So I have carbon and hydrogen present. Very good marker. Take the atoms of each, multiplied by the molar mass on the periodic table. So how many atoms of carbon are in that chemical formula? 3?
3.
How about hydrogens? 8. We're just looking at the subscripts. That tells us how many. Now for the molar mass portion, we look at the periodic table. Find carbon on the periodic table. 12.0. Is it 1 or 1?
This is one on ours.
Okay. And then hydrogen, we saw that last time, 1.008. So multiply across. All right, so I have first step, conversion factor ready. Now the second step, going between moles of C3H8 and moles of CO2, we said we needed a mole ratio. What's the mole ratio? The mole ratio, you're looking at the balanced chemical equation. So we're going to look at the coefficient in front of C3H8 and the coefficient in front of CO2.
Duration.
1 to 3.
Yeah.
Okay, more specifically, this is saying 1 mole of C3H8 is going to make or produce 3 moles of CO2. So, second step, we have a conversion factor now to get us between moles of both. We have one more step left because we don't want to stop at moles of CO2. We want to know how many grams is produced. So we need molar mass again. This time, molar mass of CO2. I don't have enough room on the board to make all of these. So I'll do the molar mass of CO2 up here, I guess. Same steps that we did for C3H8, just a different molecule. So how many carbon atoms? 1. How many oxygen atoms? 2. Go to the periodic table, 0, 1. And oxygen is 16, correct?
Mm-hmm.
44.
4.01. So it's just coincidence that these happen to be almost exactly the same, our 2 molar masses. That's grams per mole. All right, so we have 3 different conversion factors. Now we can start our railroad tracks, or dimensional analysis, I should say. What are we starting with in this upper left-hand corner?
The 1.15.
Right, the 1.15, what the question gave us. Say C3H8. And that grams of C3H8. The first step is to get to moles of C3H8 so that I can compare using the balanced equation. And to do that, I'm using the molar mass, in green here, of C3H8. Now remember, this is a conversion factor. It's grams equal to 1 mole. So do I want that 44.094 grams on the top or on the bottom?
On the bottom, yes. Grams.
The gram portion we want on the bottom,
Mhm.
right? Because we're trying to get rid of the grams.
Yes.
So 44.094 grams C3H8 is equal to 1 mole of C3H8. So grams C3H8 canceled. If I stopped here, I would have moles of C3H8, but I'm going to continue going so that I can get moles of CO2. Now for this step, it's that mole ratio, the coefficients in front of each. So, do we want the 1 or the 3 on the top? The 3. See, 3 moles of CO2. Because that's what we're trying to get, so we want that on top. And that'll put the 1 mole of C3H8 on the bottom. That way, moles of C3H8, opposite sides of that horizontal line, cancel. Now, we are at moles of CO2. We're going to keep going, that last step to get it in grams. For that, we're using the molar mass we calculated up here for CO2. So for 44.01, the grams portion, do we want that on top or bottom?
Grams on the top.
On the top? Yes, because that's what we're trying to get.
Yeah.
So 44.01 grams of CO2, that's what that number represents, grams of CO2, is equal to 1 mole of CO2. Opposite sides. So multiply all the way across, everything on top, and divided by everything on bottom. How many sig figs do we want?
3.
3, so we're looking at the sig figs in the original number, 1.15, yes.
3.44.
What'd you get?
3.44.
3.44, and that is grams of CO2, so it's the only thing we haven't canceled out. So all of that work just to figure out if I put 1.15 grams of C3H8 in the flask, how many grams of CO2 am I going to produce? Questions so far? Today we're just going to focus on doing these types of calculations, and then on Wednesday I'll bring in limiting reactants. Let's just get more practice with this first. So let's try a different balanced equation, just so you can see how it applies on different ones. You can use it for any type of balanced equation. So we just did a combustion reaction equation. Let's try a different type. I do have a supplemental material folder that has a lot of practice questions and extra videos you might find helpful. This is usually, students find this to be the hardest, the most difficult topic of the course, is stoichiometry and limiting reagents. So use the resources. ER2, this guy. Just for practice, once you get that written down, let me know what type of reaction it is.
Balance.
What?
Balance?
Double.
No?
Is it not balanced?
Mm.
We have 1 calcium, 1 calcium, 2 bromines, 2 bromines, 2 silvers,
2 silvers.
2 silvers, 2 NO3s, and 2 NO3s. Yeah.
Balanced.
So double replacement reaction. I think we did this exact one last week for balancing. Now we're going to take it and do calculations with it. So we're going to start with 8.11 moles of calcium bromide. And it's asking it will produce how many moles of silver bromide. So remember, to go from moles of one compound to moles of a different compound, we need the balanced chemical equation, and we're going to look at the coefficients, because the coefficients represent the number of moles. So what 2 coefficients am I going to be looking at?
Calcium bromide and
Calcium bromide and silver bromide. So you're going to look at the coefficient in front of calcium bromide. If there isn't one, it's just a 1. Then we're going to go look at the coefficient in front of silver bromide, and it's a 2. So if I had 1 mole of calcium bromide, I would produce 2 moles of silver bromide. But that's not the case. The question is asking, what if you had 8.11? So to figure that out, you need to use this mole ratio. This is saying that 1 mole of calcium bromide is going to equal or produce 2 moles of silver bromide. So it's just a one-step problem. Because I'm going from moles of one to moles of the other. And this conversion factor will get me there. All right, so what am I starting with? The number in the question, the 8.11. This conversion factor to get out of moles of calcium bromide and into moles of silver bromide. So am I going to want the 1 on the top or the 1 on the bottom? Bottom. That's that 1 mole of calcium bromide. Putting it on the bottom cancels out moles of calcium bromide. Puts the 2 on the top. We're just taking 8.11 times 2, and how many sig figs? 33. 10.2. 16.2, is that correct? And you've done conversions like this before with not even thinking about it. You didn't set it up this way or anything like that, but think of it like doubling a recipe, right? The recipe might say, okay, you only have 1 cup of this. Well, what if I wanted 8 cups? So now you can, instead of doubling your recipes, like 1.5 them using, most people just double because it's easy to just multiply everything by 2, but try another one? All right, I'm going to use the same balanced equation, and we're just going to do a little bit more difficult one. So let's say we wanted to make 0.52 grams of calcium nitrate. That's how much I want to make. Oops, forgetting this. So how many grams of silver nitrate do we need? So this would be more of a recipe type form, right? This is how much you want to make. How many grams of reactant do you need? In this case, silver nitrate. So let's make a plan. We're starting with grams of calcium nitrate. Where are we going to go next?
To the AG.
We want to get to silver nitrate, right? But the only way we can go between 2 different compounds is when we're in moles. So right now I'm in grams.
Yeah.
I can't compare grams of calcium bromide to grams of anything else. So I need it to be in moles first so that I can use those coefficients to compare. So my first step is, since I'm in grams, is to get to moles. More specifically, moles of calcium nitrate. Okay, once I'm in moles, now I can use the coefficients. Now I can try to get over to the silver nitrate. Okay, but I'm not going to be able to get to grams of silver nitrate right away because these coefficients represent moles. So I'm going to go from moles of calcium nitrate to moles of silver nitrate. Using the coefficients in that balanced chemical equation. Once I have moles of silver nitrate, then what? What's the last step? Then I go to grams. So let's look and see what we need for each of these three steps. So this is the hardest type because you're going from grams of one all the way to grams of a different compound. So to do that, you have to get it in moles first so that you can use the coefficients as a mole ratio. And then once you have moles of the desired compound, you can then convert it to grams. So what are we doing in our first step? What piece of information do we need? We're starting with grams and we're going to moles. So whenever we're doing these types of problems, we have Avogadro's number, molar mass, and mole ratios. Those are our only three possible choices. In this case, it's molar mass that we need. Molar mass gets us between grams and moles. Okay, so now the next step, once we're in moles, to get from moles of one compound to moles of a different compound, what are we using? Avogadro's number, molar mass, mole ratio. Mole ratio. Yeah, because these coefficients represent the numbers of moles. So this step is going to be our mole ratio step. Now the last step, we're going between moles and grams. And yeah. So, it's going to be a long one. Let's start by getting our molar mass of that big guy. Calcium nitrate. So we make a list. And when we're calculating molar mass, we do, even though this is a polyatomic, we do need to split it up into nitrogen and oxygen. I know when we're balancing, I said if you have a polyatomic when you're balancing, keep the polyatomic together. But we can't do that when we're calculating molar mass. So for calcium, how many atoms of calcium are in that chemical formula? Just one. Now nitrogen's a little trickier because you have to take into account this 2 on the outside of the parentheses. So how many nitrogens are there? 2. How about oxygens? 6. So we're taking the number outside of the parentheses and multiplying it by the subscript on that oxygen. So 3 times 2 gives me 6. Next column, we're looking at these numbers on the periodic table, or these elements on the periodic table. There's calcium 40. Nitrogen is 14 something. And oxygen 16. That one I did. Multiply all those across and then add them all together. A lot of practice with molar mass calculations today as well. At 164.1. Is that what everyone else is getting? Grams per mole. Go ahead and write it like a conversion factor, actually. Okay, so what that says is if I had 1 mole of calcium nitrate, it would weigh 164 grams on the scale. So that's going to get me between grams and moles. Questions so far? Okay, next step is our mole ratio. So to figure out the mole ratio, we're looking at the coefficients, more specifically the coefficients in front of these 2 compounds. 1 and 2. Yep, that's a 1. And then silver nitrate's here, 2. Okay. So that means 1 mole of calcium nitrate equal to 2 moles of silver nitrate. Oops, I was thinking right there. I have no room to do the next calculation. I have to erase. Yes. Last step. We need molar mass. Molar mass of what? The silver nitrate. So, I'll write it in here. Go all together. Make a list of every element present. Silver, nitrogen, oxygen. How many silver atoms do we have? 1. How about nitrogen? Oxygen? And we already looked these up. I'll write those down. What is the molar mass of silver? 107.9? So multiply across and then add all together. And that's grams of silver nitrate equal to 1 mole of silver nitrate. All right, we have our 3 conversion factors. Now let's see if we have enough room to actually use them all. What are we starting our railroad tracks with? 0.521 grams calcium nitrate. Yeah. Got a room already. All right, what are we using first? We have 1, 2, 3 different conversion factors here. First, top one. 1, 2, 3. So do we want the 164 on the top or the bottom? The 164? If we put that on the top, then we're going to be putting moles on the bottom. So let's flip it, yeah. Trying to cancel out grams, so we want to put 164.10 grams. Definitely not going on the front. And then the 1 mole will go on the top. All right, so grams cancels. Now I have moles. I'm at this step, moles of calcium nitrate. So we're going to use the mole ratio, the coefficients in front of these two, to get to moles of silver nitrate. So what do I want on the top, the 1 or the 2?
The 2.
2 moles of silver nitrate. Yes, and then my 1 mole calcium nitrate goes on the bottom, so that it cancels. So if I stopped here, I would be in moles of silver nitrate, but I want to keep going. I'm going to use the molar mass now to get to grams. So using the molar mass we calculated down here, 169. It's kind of hidden because of the that I wrote there. This was a 1. 169.91 grams on the top. So that's a lot. Multiply all the way across and divide by what's in the bottom. 521 times 1 times 2 is 169.91 divided by 164.
How many six digits? 3.
3, yep.
1.07, well, 1.08.
8 is grams. So if we wanted to make 0.521 grams of calcium nitrate, we would need to start with 1.08 grams of silver nitrate. You'd have to put in our flask. And we make this. All right. Yeah, since these take a while, I'm not going to start another one because we only have 5